Hello, everyone, and welcome to another episode of Serverless Sorcery, where we delve into the magic of serverless computing and Gen AI. I'm your host, Rinaldi, and today we have a spellbinding topic that I know many of you have been eagerly waiting for. Java has been a challenging language to optimize for function as a service platforms like AWS Lambda. Today, we're going to discuss about how we can transform these dreaded cold start times from a frustrating 11 seconds down to a snappy 100 milliseconds. To help us navigate this interesting issue, we have a special guest, Daniel Ranis Ranlan, also known as Ranis. He is a problem solver who keeps track of the bigger picture. Rennes is prestigious, likes to get into new domains, and loves sharing knowledge and ideas. He's worked with system and software architecture at several companies since 2010 and has been with Factor 10 since 2021. When not working, he's into beer brewing, sourdough bread, 3D printing, and triathlons. Rennes, welcome to the show. We're thrilled to have you
Thank you.
here to share your insights on making Java a valuable option for serverless applications.
Well, thank you. It's nice to be here.
Fantastic. So let's get started a bit by more or less recapping a bit on what we're going to talk about today. And I think I did a bit of introduction as well, but uh, do you want to also give a bit of your thoughts as well on what you personally feel that would be very valuable from this discussion to our listeners as well?
We're going to focus on Java on serverless functions, Lambda specifically, because that's where I have the most experience with it. I've been trying this with Azure recently, and I think most of this can be applied there as well. I just haven't gotten as far as actually applying it yet. I'm still working on that. But what we're going to discuss and what the problem is when your function starts for the first time, either because it hasn't been used for a while, or because lots of new traffic comes in and you need more instances of your function. Java needs to cold start. And this can take a while. In my example, which is just a extremely simple function, that it's basically a hello world function. It takes 11 seconds for new instances to start up, and that's doing absolutely zero initialization. So once you have initialization in your function, maybe you have a more complex setup. I'm using dependency injection with Spring. If you have multiple configurations and maybe services and repositories that you need to instantiate, it's probably going to take even longer. At a previous company, we had a function that started up. I think it took 34 seconds for it to cold start. And with what we're going to arrive at or discuss in this talk, we can get that down to a few hundred milliseconds.
Right. It's certainly a big issue for organizations, individuals, especially those dealing with trying to be able to better the user experience, just because it has a big impact on how the user experiences the application that way. In your
Yeah,
own experience as well, could you give us an example as well of how a cold start in one of your cases, for instance, was able to impact the user experience?
I mean, I bring up as an example. This is a fictive example, but imagine if you have a web application or a single page application served by an API, and if it has been unused for a while, say it's a fairly local. Well, let's say it serves customers in Sweden only. It's probably going to have zero traffic on nights, most nights at least. So when people wake up and they go to your single page application, every function that serves your application has this cold start. And if you use something like Amazon API Gateway to serve your API, which is based, or you can build it exclusively with Lambda functions, you will have an authorizer function, and then you will have all the functionality. And the first thing that happens is that your authorizer function has to cold start. And if that takes 10, 15 seconds, that's 10, 15 seconds before your application logic is reached. So then that Lambda has to cold start and it adds on another 10, 15 seconds. And eventually you're sitting there, your first user has to wait for 30 seconds before the first data shows up, and by that point they've probably given up, moved on elsewhere. Try again later. Maybe you lost that sale completely because they had to wait for too long. It's terrible user experience. And if we can reduce that down to where it's basically instantly, I don't recall, but I think I read somewhere that anything that is more latency than half a second is noticeable. Beneath that is essentially not noticeable. You click a button in the UI and something happens after 400 milliseconds, you're not going to think about that. If you click a button, it takes 800 milliseconds or a second. That's noticeable lag, and it will be annoying. People might try clicking again because nothing seemed to happen. And you will get all sorts of other issues with race conditions and double orders and all that.
Definitely. I feel that as backend implementers, one of the things that we often fail to take into account is really how impatient a user can be on the front end, which I think is quite evident as well from what I do day to day too. I work with a lot of different third-party tools like Datadog and pretty much, for instance, like CloudWatch, and we always try to keep track of this metrics and try to better the latency that these Lambda functions take and the overall user experience, because oftentimes it's not only the Lambda function that will be causing the bottleneck, but also many processes along the way too, because it's often part of one big architecture. And that's why it's best to reduce bottlenecks on the Lambda itself as much as possible, because it usually already contributes quite a much if it's not taken care of properly. But on the point of Java, I think it's good if we drill down a bit as well, more into the Java side of things. And oftentimes, I feel like Java's comprehensive libraries and runtime optimizations come with the larger trade-off of longer initialization times, which I think usually can be a challenge as well within, say, serverless environments. Do you have any thoughts as well on some of the why Java in particular might be suffering this more compared to like other runtimes in particular?
Yeah, and it is because so Java does two things. If we're talking about a common Spring application, there's three things that happens. And like if you go at this, if you look at the problem naively, you might think that because when Spring starts up your application, it goes through your entire class path. It checks all your class files and looks for annotations that it will figure out how to dependency inject your application so it gets up and running, right? And so you might look at this and think that, well, this might be the problem, because I know from experience that Amazon Lambda at least has fairly slow disk access. So if the jar files are stored on disk and you need to scan through the jar file, you're scanning a compressed archive from disk that could be kind of slow. So maybe that's the issue. So one thing I tried was to switch out Spring for Micronaut, which does all the analysis during compile time. It hooks into the compiler, and instead of scanning your class path when it starts up, it does all of this when your application is compiled. So you can skip the entire analysis stage in the startup, and that does save some time. It saves in my benchmarks with my extremely simple function. It saved me 1.5 to 2 seconds actually, which is, that's a lot. But it still only brings us down to 8 seconds, or 4.5. And if you're running a later JVM, they've done both Amazon and Oracle, I guess, have done steps to reduce the startup time of Java, and they're progressing further. But even if we're talking 5 seconds, it's still this is still a long time. Still, it's 10 times longer than the 500 milliseconds we discussed before. So the next thing you start to look at is, well, what actually happens when the JVM starts up? Well, what happens is that it reads your class files, and this is the Java bytecode, right? And Java bytecode is what we call an intermediate language or intermediate format. This is not something that your processor can execute. So what needs to happen is that this bytecode that the JVM understands needs to be translated into something that your CPU understands. And depending on if you run on an Intel or an ARM machine, or even if you run AMD, which is like it's the same instruction set as an Intel, right? But there are slight differences in what instructions they support, especially when it comes to extensions. So it does a just-in-time compilation. It takes your bytecode, turns it into machine code, and it does that whenever it finds a new class file. So when you start your application, it probably has to load thousands of class files, and it needs to do this compilation from bytecode to machine code for all these thousands of classes that it's loaded. And this happens even if it's a very simple function, because all of the JVM needs to do this, and all of your classes. And if you use something like Spring or Micronaut, there's a lot of classes around this that also needs to be just-in-time compiled. And this is what takes the brunt of the time at startup. And
Right.
if you look at other languages, this doesn't happen in the same way. I know C# has had issues with this as well. I haven't done a deep dive into this to see if it's as bad as with Java, but I know there has been. I've seen reports and measurements that there can be a significant cold start issue with C# as well. But if you look at other interpreted languages like JavaScript and Python, they do things slightly differently. I mean, Python is an interpreted language, as far as I know. They don't actually do this just-in-time compilation. They parse your application that happens. So that means the Python is faster to start up, but once it gets running, Python is slower to execute. It's probably not that noticeable in a Lambda function, which, I mean, they tend to be sort of glue in your application. They do a lot of data shuffling. They deserialize, they change some things, serialize and put it into a database, or they offload into a queue or something. So you probably won't notice it, but I know this has been talked a lot about. One of the benefits of Java is the just-in-time compiler, because it can actually, once your application has been up and running for a long time, it can re-optimize the machine code is generated based on how the application is actually executing. So it has potential to increase performance the longer your application is running. And you don't get that with the languages that don't do this. So it's a trade-off. You trade startup speed for eventual speed, or longer runtime performance. And that's the whole issue here. But so what we really want to do is we want to have Java be quick, and then maybe not do these optimizations in the future. Or maybe we can even find a middle ground that can do both. And if we look at
Definitely.
other languages that are actually compiled, such as, you can write Lambda functions in C if you want to. I do prefer, I use a lot of Rust if I run Lambda functions these days, because the Rust ecosystem has evolved and there's a good runtime for it from Amazon, actually. Even if it's not I don't think it's officially supported runtime, but there is a community project maintained by Amazon for running Rust functions on Lambda, and it's insanely quick. When I did my benchmarks, a function with similar functionality to Java, Rust was actually faster to cold start than Java is when Java is warm. So if you have a Java Lambda function that has been it's been cold started already, it's up and running, and you make requests, I think I had like 140 milliseconds or something of response time, and my Rust functions cold started. Like, there's no function running; it needs to cold start. It needs to run as start and then serve your request. It took 80 milliseconds. So
Right.
Rust is insanely quick. But I guess the trade-off for that is that you need to learn Rust, and Rust has significantly longer compilation times if compared to Java. I mean, a Java application compiles in 8 seconds, can take 5 minutes to compile in Rust.
Right.
And it also means that the Rust application is non-portable. So the Java application, you can take the jar file and you can run it. You can trivially just change the deployment from an ARM server to a Intel server, or the other way around. But with Rust, you need to recompile for the specific target. You need to know your target. With Java, I think the term is write once, run everywhere. Um, So you lose some flexibility. You need to learn a new language, which can, I mean, it can be a fun side project to learn Rust. But there are trade-offs to using these faster languages.
Right. I feel that certainly the Rust community has been growing quite a lot, I feel, especially in terms of dealing with these challenges. I'd say that in terms of documentation, there's definitely much more uh, probably existing documentation dealing with these techniques with Java, but at the same time as well, I feel that the Rust community, because of how active it is, has been really helping as well with being able to come up with new techniques and come up with new ways of being able to deal with these optimization problems. And I think that's also a reason why there's been a huge support as well for Rust and dealing with these sorts of issues and being able to provide great insights for dealing with these issues. I I want to backtrack a bit and focus a bit as well on what you're mentioning as well on benchmarking, because benchmarking is a very important thing, I feel, for a lot of users, especially in measuring cold start latencies, as you were talking about earlier, considering different factors like memory allocation, initialization times. And in your experience, how do you benchmark the performance of different techniques for reducing cold start times?
So benchmarking cold starts is, I mean, you can't just fire at the function, right? Because then you will get mostly warm results, which will skew your results. We're really interested in cold start. So Amazon does actually help you here. I don't think they do it because it's supposed to be easy to benchmark, but they're actually Amazon is very good at providing data, monitoring data. So what I've eventually figured out I could do, because my first approach to benchmarking cold starts was to publish a new version, to deploy the same version of the application or the Lambda function, and then just because then you shut down all your instances and then you don't start a new one. So you just you run a deployment and then you fire off one request, and that will give you 100%. That will be a cold start, and you can note that down and you can deploy again. But this takes a lot of time deploying the function. Even if it's just uploading the same jar file and waiting for Lambda to tell you that the function is now ready for execution, it takes 2 minutes or so. So if you want some significant amount, I settle on 200 to get some sort of statistic. I don't know, statistically accurate data. I mean, if every request takes 11 seconds and then it takes 2 minutes between every request, it's going to sit there for a very long time. So what I eventually figured out is that you can just change an environment variable because it changes the deployment, but and it shuts down all the functions. But the redeployment or the wait time before you can run your application again is a lot quicker. So that takes just maybe 10 to 15 seconds between every attempt. And then I also changed the method. So instead of just running one request and getting that back and then doing it all over again, I fire off, I think, 30 or 40 requests. And because, so when you call a Lambda function, you can tell Amazon that you want detailed metrics to be returned with the response. And they actually tell you if it was a cold start in that response. So you get you get the timing for the execution of the function. I guess you can use this for cost calculations, because the times they return to you are the times they use for calculating how much you should pay. I mean, that's a runtime they charge you for, and you charge you differently for the startup time and the runtime. So if you have they call it initialization time, I think, in the response. So we just keep all the responses that had an initialization time. If it doesn't have an initialization time, I think it's missing from the response. Then it wasn't a cold start. But if it has that set, we know it was a cold start. So we can just count those. So we fire off like 30, 40 responses, and then we keep going. We change an environment variable that resets the function, kills all the running functions, and we fire off another 30, 40 requests, and we keep going until we have our 200 cold starts. and that's actually a lot quicker.
Right.
Um, People who have been following along with Amazon Lambda are thinking, well, hasn't Amazon solved this with SnapStart? So the SnapStart that's Amazon's solution to this, and I think it's really clever. I do this as a conference talk. I talk about this, and when I saw the announcement of that, I was thinking, well, shit, Amazon just killed my talk. There's no point in this. But then I started investigating, and there's still some nuance. SnapStart. So what they do is, I think it's really cool. You have you ever played emulation games?
Yep.
You know how you can press a key combination and you get a save state where you can
Yes.
reload. And for a terrible boss fight or something, you make a save state and you make an attempt, and instead of just replaying the whole level, you just reload your save state. So Amazon Lambda SnapStart is basically save states for your functions. So what they do is because Lambda now runs on something called Firecracker VM, or just Firecracker maybe. It's a micro VM runtime written in Rust. Speaking of Rust, and what they did, they implemented snapshot functionality into this. So what they do is they start up your function, and so they reach the point where the function is in a state where it could retrieve a request, but they don't send a request. And then they just take a snapshot. So they make a save state of your function when it's been started. So all this JIT compilation has already happened. They save state that, and then they just do, whenever they need a new instance of your function, they just restore that function into a new VM. So instead of starting your application up, they just clone the snapshot, and it's up and running. So potentially they just need to materialize the VM as you do when you reload a emulation save state, and it's good to go. And it works fairly well. I got down to at the first attempt, I think I saved like 1 second or so, and I was a bit confused. So I was at a conference, and one of the solution architects working with Amazon Lambda was also there. So I spoke with him about it, and together I had my suspicions of what was wrong, but he confirmed it and told me that, well, you need to initialize everything. So you can implement an interface in Java, and that hooks into the snapshotting cycle. And so you can implement a function that is called before Lambda snapshots your function. And this allows you to make all the initialization. So what I didn't do in my first attempt was that I didn't make sure that all classes were loaded when the snapshot was taken. So what you do is you basically need to dry run your entire application in this snapshot method. So all classes have been loaded, and all the just-in-time compilation has happened. So once I did that in this initialization function, pre-snapshot function, I loaded all the classes, I constructed all the SDK clients, and made sure that I could do JSON serialization and all that. Basically, just running your function without it actually doing anything. Then I got it down to, I think we came down to around a second, which is, I think it's fine just for I mean, basically you just check a checkbox in the UI, or set a parameter in your infrastructure as code, and you get down to a second, which is really good. But it also comes with the drawback of you need to make sure that you initialize everything. So there's a bit of trial and error, and if you change the functionality, you add some new functionality, or maybe you even change out some parts, you change out the library for another. You need to remember to make sure that you call all these and load all these classes in the pre-snapshot function. Otherwise, you will have a performance regression. So you could, if you don't have proper checks for this, you could deploy a new function and your performance will be 2 or 3 times as bad. So it's a bit volatile, but it's a really cheap solution, and it kind of works. I mean, still a second is okay, but it's still more than these 500 milliseconds we were talking about before. So I think there's more to do there. But I think SnapStart is still a good option. But the real solution here is to go to something that prevents the just-in-time compilation from happening, and that is Graal VM. So, are you familiar with Graal VM?
I've heard of it. Yeah.
Yeah. So I think it's really cool. It started out with like the mission was to create a Java runtime that was written in Java, and in compilation circles we call that it's self-hosting. So C is a self-hosted language because well, I guess the language isn't, but let's say the GCC compiler is self-hosting because it's written in C and it compiles C, so it can compile itself. That's a self-hosted language or self-hosted runtime. So the Python runtime, the official Python runtime, C Python, that is not self-hosted because it runs the Python language, but it's written in C. So for a language to be self-hosted, you need to have a compiler that compiles down to machine code. You can't have a VM because then you will have a sort of infinite recursion going on. You need to run your VM in a VM that runs in a VM, and eventually something will need to break that cycle, and it needs to be something that's compiled down to machine code. So what they set out to actually write a runtime in Java and compile it to machine code so that you can write the Java runtime in Java. You would gain a lot of benefits because right now, like if you write a runtime in C, you're in a memory unsafe language, right? A lot of bugs related, or a lot of security bugs are related to memory management in C or C++, where it's essentially manual. Whereas in Java, you have a garbage collector and all these nice things that saves you from messing up the memory. But it turned out to be a bit of too much work, so they settled for just making a native compiler for Java, and that's what Graal is now. So Graal VM today is a distribution, and it ships the OpenJDK. So you can use it just as you use OpenJDK, but it also ships a few things on top of that. One of them, I think it's called libpolyglot, which is a language for. I mean, instead of writing like microservices in different language, you can actually write parts of your application in different languages. You can, I think it supports Python, JavaScript, and Ruby. So you can write parts of your application in Python or JavaScript, and then tie that together in the same VM. So you can have Java call out to JavaScript and the other way around, which is pretty cool. I've never actually used it, but I mean, mixing languages inside a VM sounds pretty cool. But then the big one for us here is Graal, which is the compiler, and it takes your Java application and it compiles it to native code. So it does the Rust just-in-time compilation, but ahead of time. So we call it ahead of time compilation, and that means that you now have a machine-specific binary. So it's not write once, run everywhere anymore, because you need to compile it for every specific target. There are tools to help you do this. For example, if you're on Windows or Mac OS, you need to compile it on a Linux machine to target Amazon Lambda, which runs on Linux. And there are tools, both Spring and Micronaut have toolings that does this for you. It starts up a Docker image or a Docker container, compiles in there, and it also takes care of installing all the tooling you need to do this. And you end up with a binary that you can deploy to Lambda as a custom runtime. And when we run this, in my benchmarks, I got down to, I think the latest. See, I have the benchmarks here somewhere. Let's see. It's this one, I think. Yeah, we're down to 100, 200 milliseconds cold start time, and so that's we're at a point where it's basically you won't notice if it's a cold start or if the function is already warm, which is the intention here. Like that's the goal.
Definitely. I feel like it's certainly a big challenge, especially among, since you mentioned C as well. C is a challenge in itself, I feel, and that's one of the things because memory allocation already makes the whole process of trying to remove the bottleneck much harder at the get go. So it's definitely a very interesting thing to consider. But since we talked about metrics as well earlier too, we talked about initialization times, we talked about the response times as well. Do you think there are any, in your experience, do you think there are any more important metrics that you also like use day to day to take a look at monitoring the performance and keep track of as well?
Uh, Not really, no. I mean, once you have the cold start down, so that you have essentially predictable performance. I don't really optimize my functions before they become a problem. And in a modern, especially in a function as a service deployment, you will have a lot of network latency. That's probably where you should focus. If you want to optimize, if you think your like end to end is taking too long, it's probably because you have too many functions involved. I know there was a blog post like a year ago of the Amazon Prime Video team. They redid their whole architecture, and they were using Amazon's, I think it's called State Machine, which is it's a state machine orchestrator where you use Lambda functions, and you basically you draw up your state machine, your flow, and you fill out all the functions with Lambda functions, and it automates calling that. And so your they were they were doing video encoding, I think, or some sort of processing. It could be metadata extraction or something. But so we bubbled through the state machine, calling a lambda here, calling a lambda there, and then the orchestrator went back to it. And they rewrote this from a function as a service state machine architecture into, I think they had a single container that took care of all the processing. And they found that this was 10 to 20 times faster. And immediately when I looked at this, and it was, yeah, that's pretty obvious. You went from something that does one thing with 15 Lambda functions into something that where all the processing happens on the same machine in memory, and that's obviously going to be a lot faster because you don't need to have all these synchronization points and handovers between functions. And every handover, it's network latency. And I mean, we can measure processing times. We can measure those in microseconds or even nanoseconds. But once we hit network, we're starting to talk about milliseconds again.
Definitely. And let's navigate a bit as well towards the future of how you see the landscape playing out as well. I feel that it certainly will be a very interesting future because, as you mentioned before as well, we have Amazon as well, doing a good job as well and being able to support these. And like there's been constructive discussions I feel with the AWS folks as well on how they're able to provide more support on this and looking to be able to help more communities better optimize their process as well, provide best practices. But from your end as well, what do you see as the future of Java within serverless computing environments? And do you think there are any upcoming trends? Do you think that will help improve Java's performance on these kinds of platforms?
I think the future is Graal VM. That's the I mean, it solves the cold start problem, and this is not only for functionless or for functions as a service. This is also when we're talking serverless containers, or even if you move into Kubernetes. Graal VM has a performance edge when it comes to starting up your new applications. Containers aren't that sensitive to cold starts because they happen way less often. I mean, a function can only serve like one request at a time. Whereas a container, if you run it in Kubernetes or if you deploy it using some orchestration with Amazon Fargate, or I think you can actually run your Kubernetes clusters with Fargate nowadays,
Yeah.
you will typically have one container serve many requests, as we did back in the old days when we used servers. And so that means that cold starts happen maybe probably like hundreds of times more often in Lambda functions than in other serverless setups. But still, I think the predictability of Graal VM upstarts is a major benefit. And so the problem is that Graal VM needs to compile your application. It needs to know a lot more about your application that Java figures out on startup. So you can get some really confusing error messages if you try to compile your Graal VM application, if you try to compile your Java application with Graal VM. Spring and Micronaut, and I should mention Quarkus as well because it's a different dependency injection framework. It comes from Red Hat. It does things. So Micronaut and Spring are very, very similar in how they work. If you've used one, you will instantly recognize yourself in the other. Quarkus does things a little bit differently. It's not a major difference, but it's enough that there are people who prefer the Spring and Micronaut way and people who prefer the Quarkus way. But performance-wise and ecosystem-wise, they cover your bases. If you need something that's probably in their ecosystem, there's probably a plugin or a component for whatever you're trying to accomplish. But all three of these handle a lot of the metadata and all that you need to tell Graal VM about. And this is things like because Graal can actually, it's pretty cool. It can initialize some of your classes when it's compiling. So some of the things that you have static fields, it can actually compute the value of the static field. So it isn't computed at startup. It's just ready. So when it loads the class, it's already there in memory. But it needs to know which of these initializers should happen in runtime and which should happen in compile time. And that's provided by a lot of JSON files that contain this metadata. And Spring and Micronaut and Quarkus, they provide a lot of this metadata for you, so you don't need to think about this. But if you start down to write a Graal application from scratch using none of these languages, or if you need to move outside of the ecosystem and use something that there isn't a module or a component for, you probably will need to write these specifications on your own to tell what should be included and what not. And there's also the thing with reflection. So Java, I think for me, one of the strong points of Java is the reflection. You can do a lot of crazy thing and you can do a lot of bad things with reflection. But you can also do a lot of powerful things with reflection that removes complexity and especially removes like code repetition. You can do a lot of things towards dry with reflection. But the thing is that since Graal compiles now, there's no runtime in Graal. Graal runs as a native binary. There is no JVM around this that keeps track of all these metadata that is required for reflection. So this needs to be baked into every class file. And that doesn't happen automatically with Graal. You need to tell Graal which reflection data should be included when it's compiling. So if you run, say, something like Jackson, which does JSON serialization, you can use reflection. You can use field reflection to serialize your data. If you don't tell Graal that this class I have here should include fields as reflection, Jackson will not find anything to serialize. So if you run your tests and you run them on a regular JVM, you will get proper JSON serialization. But once you compile it with Graal and then you run it in production, you will just get empty responses because Jackson didn't find anything to serialize. Because when it asked about, I want all the fields of this class, Graal VM didn't include that. So it just got an empty list and then just returns an empty object. So there's some pitfalls with this you really need to think about. So the complexity of writing your application increases a lot. But I think if you do this from the start, if you write your application with Graal in mind, you continuously test also on Graal, which is something that, I mean, naturally you want to test on the JVM because you get the fast compilation times, you get the fast feedback loops. Graal VM is a lot slower to compile, a lot slower. We're talking Rust levels of compilation, something that takes 5 seconds to compile to bytecode. Maybe takes 2-3 minutes with Graal. And that's also because Graal needs to compile all the jar files that you pull in, all your dependencies. Graal needs to turn those into native binaries as well. So obviously, there's a lot more to compile, because when your Java compiler compiles your application, it turns your Java files into class files, whereas the Graal compiler needs to turn all the class files in all your dependencies, as well as your class files, into native binaries. It takes a lot longer. So it's kind of, if I develop Graal applications, because I do test-driven development. I do my test-driven development on the JVM, and then I run my tests. Typically, you do it in a pipeline. You compile with Graal, and then you run your tests in Graal as well to make sure that you haven't missed anything. If you think about this and get used to it, it happens seldom enough that I think it's enough to run those in a pipeline, that just for a safety net. You don't need to run all your tests all the time in Graal. You can get by with just working on the JVM and verifying on Graal before you merge it into your main branch. But I think
Beautiful.
that's where the future is. Graal VM, definitely.
Definitely. And I would encourage our listeners to look into it much more as well. It's certainly a great tool to be able to further deal with this. And so we're coming up to the end of the episode, but before we depart, Ranis, is there any particular final advice you would give to developers who are struggling with cold start issues within serverless applications?
Yeah, there is. I mean, I think the absolute first thing you should do is to figure out if it's actually a problem. Because I've had I mentioned a Java function that took 30 seconds to cold start. What I didn't mention that this wasn't a problem. So this was an internal function that we used to analyze data from the production environment and produce a report, basically, that we looked at on our daily stand-up. This ran sometime during the night, let's say at 4 in the morning, and we only needed the results 5 hours later. So if we had 30 seconds of cold start time, it doesn't really matter, because it ran in, I think it ran in like 5 minutes, took 30 seconds to start. It doesn't matter. No one was actively waiting on this Lambda function to start, because it only ran once every night. It was a cold start every time, of course. But that wasn't a problem. So in that case, you just leave it be. Because yes, you're paying for the cold start time, but you could probably run this function with cold start times for 20 years every day, and it still costs less than what it costs to have a developer fix it. Because server time is a lot cheaper than people time. So the first step, I think, is to figure out if it's actually a problem or not. And then I think you should try solutions in complexity order. So the first thing you should try is probably snap start. And if that works for you, if you get it down to an acceptable level, just run with that, because that's a really simple fix. But if you really need this performance out of it, you should consider either rewriting in a different language, Rust, Go, even Python, or JavaScript or TypeScript. But if you really need this performance and you want to stay on Java, then you need to go to Graal. You need to have a native binary with Graal, and it can be really easy if you use modern Spring or Micronaut or Quarkus and stay within that ecosystem. Hopefully, it's just a matter of compiling it with Graal, which there is tools. The Gradle and Micronaut plugins and Quarkus plugins for Maven and Gradle help you do this out of the box. You don't really need to set anything up. You just get a compiler target and you tell it to compile native, and you get a native binary. So it can be really, really easy, depending on, of course, how complex your code is.
Definitely. Beautiful. And I think that's a great closing to our sixth episode of Surreal Sorcery. Thank you again so much, Renis, for sharing your expertise and insights with us today.
Well, thank you for having me. It was a pleasure.
So we've journeyed through the challenges and solutions of reducing cold start times for Java on AWS Lambda with Redis, and we've managed to understand the basics of what functions can do to be able to then explore various optimization techniques and finally see how we can achieve those impressive cold start reductions. So it's been an overall really enlightening session. And to our listeners, if you've enjoyed today's episode, be sure to subscribe to The Real Sorcerer on our platforms, which include Apple Music, Spotify, and YouTube. And do leave us a review. And we always love hearing your feedback and suggestions for future topics. And feel free to also follow our LinkedIn at Surveillance-Sorcery. Runnis, if anyone wants to reach out to you or ask you any questions as well, what's your best handles to for them to reach you at?
I think LinkedIn is the best way to reach me. I am on Mastodon, but I'm not there very often. I forget to check my Mastodon. But I am on LinkedIn as Daniel Ranis Raneland. You can probably search Ranis with a Z, Ranez, and you will likely find me.
Beautiful. Thank you so much, Rennis. And again, to our listeners, thank you again for tuning in. And until next time, may your functions always be faster, cold starts forever short. And yep, this is us signing out now. Thanks all.